Hi, my name is Valerie Zammarelli, and the date today is 2/29/24. Today I will be going over how to find the center of mass for R1. This is a unique case because I also found the center of masses for R2 and R3. For R2 and R3, I could use the center of mass equation equaling to mass over area and get my answer. R2 and R3 are set up more like rectangles, so they're a little bit more simple to solve as compared to R1, which is a ring, and in this case it is a semi-ring, so it's only half a ring, and because of this, we will need to use integration. So first, to start off the process, we have linear mass density. So for linear mass density, lambda equals dm over dl, which equals m over l, which equals dm equal to lambda dl. Now, why did I solve for dm? Well, later, as we will see in the integral, we will have a variable of dm. This will make it more simple to then plug right in lambda times dl. Next, we have our angle. Angle equals L over R2. Now, what is R2? So, for our center of mass that we are finding for R1, we have an inner radius and an outer radius. The inner radius representing little r1 and our outer radius representing little r2. We want to use that outer radius. So we have the angle equals L over outer radius. This then also equals d theta, which equals dl all over d, our outer radius, or r2. We then want to solve for dl. The same reason why we solve for dm, we will be able to see how we can directly plug in what dl equals. So dl equals r2 d theta. Now if we move over here, we have our integral. Our integral, we are solving for the y center of mass. This is because our x center of mass can be disregarded for now because our x center of mass is equal to 0. For our y center of mass, this equals to 1 over m times the integral dmy. So as you can see, we have dm. Where did we solve for dm? In linear mass density. So dm equals lambda times dl. But wait, we also have what dl equals to, as we found from the angle. dl equals r2 times d theta. So combining both of these equations, we can see that dm equals lambda times r2 d theta. That lambda r2 can be pulled out to have lambda r2 over m integral of y d theta. Now we could take this lambda r2 all over m, and we can simplify this to 1 over pi times the integral of our y d theta. So now we have 1 over pi times our integral, but now we have our bounds, and we are going from 1 to pi. We want to plug back in our r2 value, and we have now for our function sine theta d theta. This theta tells us that we need to take the antiderivative. We want to pull out r2 to have r2 over theta and be left with just our sine theta to find the antiderivative of. The antiderivative of sine theta is negative cosine theta. And again, we have our bounds going from 0 to pi. When we have negative cosine pi minus negative cosine 0, we reach a value of 2. So now 2 can be multiplied by r2 all over pi. Now, as we can see in the project 2, our r1 value is equal to 25, but that's our inner radius. We want to use the outer radius. So our r2 value, the outer radius, is equal to 35. So now we have 2 times 35 over pi, and 2 times 35 leaves us with 70 over pi equaling our R1 center of mass. Thank you.